Okay, so when you open the Desmos graphing calculator app, for that you need to put in this URL, desmos.com/calculator, because Desmos as a company has more offerings apart from the graphing calculator as well. Okay, so when we come here, this says untitled graph, and here we need to input the equations or the functions which we want to graph, and they would appear right here on the grid. The grid can be zoomed in or zoomed out by the plus and minus icons. Okay, so I've zoomed out right now, and right now the scale is 1 unit per block, per square block. It's a 1 unit. Okay, when I zoom in, it goes to further smaller units. Okay, so now let's try, I'll show you a very simple example first of all to see how to write a function. You can directly write, let's say you want to write y is equal to 3x plus 4. You can directly write 3x plus 4. This in itself means y is equal to 3x plus 4. Or you could write y is equal to 3x plus 4. Okay. Or you can write f of x is equal to 3x plus 4. All ways of writing are acceptable here. They are understood by Desmos. So it's presenting you the graph of 3x plus 4. We can see from the equation that y-intercept is going to be 4 when we put the value of x as 0. As you can see, that's here, 0, 4, shows the point there. Okay. And the x-intercept is shown at negative 1.33, 0. Negative 1.33 because when you put y is equal to 0 on our equation, x is equal to negative 4 over 3 or negative 1.33. This is how you represent a basic function on Desmos. Okay. Next, let's try to sketch a quadratic function. Okay. I'm not going to change much. 3x squared. So putting the square, you just do the power symbol, which is basically on the key number 6. You press it with the shift key, okay, to get that, and then press the right arrow key so that it comes to the original. Otherwise, if you keep typing after the 2, it'll keep writing there itself. You see, like that. So you need to press the right side arrow key so it'll come back to the original expression. So 3x squared is right now written. Then you will write 4x, let's say minus 6. We write this. Okay. So as you can see, the graph is sketched here. I'll zoom out a bit so that the complete graph is visible. For zooming out, you can either use this zoom out and zoom in keys, the plus and minus symbols, or right on your trackpad, you can just pull your 2 fingers apart. It'll zoom in. If you put them converge the 2 fingers, it'll zoom out. Okay. So right now we want to zoom in just slight bit so that we can see the important points. Okay. Now you can see the graph. If you want to see the critical points, like where's the root, where's the vertex, for that just click on this red area of the graph. I click on the red area, it shows 4 different points. This is the first root, negative 2.23. Here's another root, 0.89. Here's the y-intercept, where the function, the quadratic equation, is cutting the y-axis, 0, negative 6. As we can see directly from the equation, negative 6 is there when you put x is 0. This here is the vertex, negative 0.667 and negative 7.33. This is the vertex. So you see, this is such a fast way of getting all those points. If you're given, let's say on the test, you're given a quadratic equation and they're talking something about its roots. Let's say they ask the sum of the roots. You would first be writing the quadratic equation and then solving it. Better than that, just put it here on Desmos. You get the roots directly. And then addition is like a minor task here, from here. Okay. Or you don't even need to add them. If you're given the vertex of, the coordinates of the vertex, the x coordinate is given here, negative 0.66. What is the vertex? It's basically the x coordinates of both the roots summed together divided by 2. Because it's the midpoint of both the roots. Okay. So the sum divided by 2 is negative 0.66. That means the sum is 2 times negative 0.66 or 1.22, 1.32. Okay, negative 1.32. So this is how you sketch the quadratic function on Desmos. Okay. So we can see a few more functions as well. Let's say there's a complex function, for example, 2x raised to the power of 4. Now, 4th degree polynomials we cannot deal with directly like with manual mathematics or factorization or any formulas. So for that, this would come really handy. Let's say 3x cubed minus 14. Okay, let's see how the graph looks like. Looks like this. It's giving us the critical points, first root, second root. Then this is here, the y-intercept. This is sort of a vertex. Okay, for this fourth degree polynomial. Let's introduce the x squared and x cubed, x squared and x terms as well, so that you get more roots. So 2x squared plus 10x minus 5. Okay. Now when we look at the curve of this, what are the points it's showing? Here are the roots, 1, 2, okay, this is the y-intercept, and here's a vertex. Okay, so even if you don't know the nature of the curve, just by keying in the equation, this gives pretty accurate results. Okay, now the important thing, where else can you use this calculator? It's not just for graphing, it can even be used to solve equations. What if you're given two linear equations, 3ax plus 5, this is the first equation. Now the important thing is, we'll see how to key in two separate functions on a single screen here. So go to the next one, click on this next, it'll automatically form a box. So I go on 2 and I write y is equal to 4x minus 3. Okay, it's graphing the second one in blue, the first one in red, so that it's distinctly visible. As you can see, you can find the intersection point directly by clicking on any one of the blue or red curves. I click on red. This is the point of intersection, 8, 29, and voila, this is the solution. You got it. Here the y-intercept of the red one, the x-intercept of the red one. Similarly for the blue one, when you click on blue, it's the y and x here, but both of them would give you the point of intersection. Perfect. Okay. If you want to find multiple points of intersection, let's say we talk about 3 different lines. Y is equal to 6x plus 15. So you see there are multiple intersection points. First one between red and blue, then second one between red and green, then third one between blue and green. All coordinates given exactly here. Okay, let's make this a bit more complicated. Let's say you have y is equal to 3x plus 5. This is 1. And next I key in a quadratic, because a lot of times you would get the system of equations, especially when you look at the topic, the nonlinear equations and system of equations. There you will get different kinds of functions. So y is equal to, let's do a quadratic, x squared plus 5x minus 14. Okay, see how beautifully it has given all the solutions, all the critical points. This is one intersection point, the other one is here. It's intersecting at 2 points, the line. And for the quadratic equation as well, it has given us the roots, the y-intercept, and the vertex. So directly identifiable from here. Quadratic with linear. We can even do quadratic with quadratic. Let's try that. So the first quadratic that I've written, x squared plus 5x, there's a parabola opening upwards, as you can see. Let's take a parabola opening downwards. Negative 2x squared plus 5x minus 12 or minus 19. No, let's do a plus 4. Okay, see the two quadratics, they're intersecting. They would be intersecting at 2 points. We can see the coordinates of each. Click on red, you see these two. Then the roots of the red, these two are the roots. There's the y-intercept, there's the vertex. For the purple one, click on purple, the intersection points would be the same. These are the roots for the purple. This here is the vertex. Okay, it also happens to be the vertex. So look, this is so beautiful that we're having the vertex is almost same. Okay, 2. Let's check how is one of the intersection points coming on the vertex. Purple one has its vertex here. What's the vertex of purple one? Negative b by 2a, minus 5 upon 2. Okay. And it's sharing an intersection point. So minus 5 upon 2, that's, yeah, negative 2.5. As you can see, that's correct. That's also the point of intersection. So that means this is getting satisfied by this curve as well. Nice. Good to see that. Okay. Okay, so this is a quadratic with a quadratic. Now, similarly, you can choose any function. There are no limitations. Y is equal to x, as you can see, it intersects. Let's do some exponential and logarithmic functions. How to write the exponential function? Let's say 3 raised to the power x. Y is equal to 3 raised to the power x, and I do y is equal to x squared as the second function. Okay, let me zoom it out so you can see. Okay, I click on the red one, the exponential function. At x is equal to 0, it would be at y is equal to 1, because any number raised to 0 is a 1. So as you can see, 0, 1, and it's intersecting the quadratic here. So to solve this manually is a tough task, but on Desmos you have the coordinates directly. Okay, another very important, so right now we've seen how to sketch a single graph, how to find the points of intersections when there are multiple equations. Okay, next one we're going to do is a parametric analysis of graph. So what does that mean? That means, let's say you have a function, a quadratic function, let's say ax squared. Here a is not known. Ax squared plus 4x minus 9. Okay, this is the function. Now Desmos automatically gives you an option called add slider as soon as it sees a variable getting taken in the equation. A is a variable. I'll say, yeah, okay, let's add the slider. So now, as you can see, I'll zoom out. Okay, this is the curve right here. At a is equal to 1, it has taken the point a is equal to 1. Okay, next you can use the slider to change the values of a to see how the graph changes. See, as I increase the value of a, the graph is shrinking vertically. There's vertical shrinkage. So for the same x value, the value of the function is increasing. Why? Because it's getting multiplied with a, whose value itself is increasing. So it's shrinking vertically. As I take it to the left, I decrease the value of a. It's expanding. It's going in horizontal direction. It's expanding horizontally. See? And the moment a crosses 0, at a is equal to 0, it's a straight line because the x square term is gone. Just a linear term. The moment I push from there to a negative, it becomes a parabola opening downwards. So like this, you can use sliders to see the nature of the curves. Okay, I could add further variables. Let's say I do this x as b, this 4 as b. Now this becomes, okay, I click on add slider. I have 2 sliders now. Okay, let's see the behavior of the curve when we change both of these. So I'm increasing b, keeping a constant. See, as I increase b, the value of f is increasing because it's contributing to the value. It's getting multiplied with the x value and it's increasing. Okay, now keeping the b same, I increase the a. Moment I increase a, the nature of the graph changes. It becomes a parabola opening upwards. Now let's increase the b. As I increase the b, it's going down. The graph is going down. Basically the vertex of it is going down. Okay, next. Okay, similarly we can take any number of sliders to see the nature of curves. I'll show you a really nice thing here. Let's start with a complex function, more complex function. Okay, so as you all know, in my videos also you've seen, in functions part 2 you've seen the interchangeability between log and exponent function. Let's take an exponent function, a raised to the power x. Okay, this is a function. Next, we take a log function. So first of all, let's see this. I'll add a slider. A is equal to 1. At a is equal to 1, the value of the function will just be 1 throughout, because 1 raised to power any number is a 1 itself. Okay, now I start increasing the value of a. Look closely. Okay, right, you see, this is why it's called exponential increase. It's increasing so wildly. Okay, it's nearing almost the y-axis. That means it's almost vertical increase. The rate of increase is so high. It's almost vertical increase. Okay. And when I start decreasing, let's come to a is equal to 1. Okay. Now I go below 1. That is, let's say 0.5. So as soon as 0.5 starts getting raised to a number, you'll see a different nature. See, the values are decreasing now. Suddenly, it becomes a decreasing function. Why? Because as you know, a number less than 1, when raised to the power, as you increase the power, the value will decrease. 0.5 raised to power 1 is a 0.5, but 0.5 squared is 0.25, which is less than 0.5. Okay, so the numbers are decreasing. So this function suddenly becomes decreasing function. It will hold this nature till a is equal to 0.1. Okay, soon as I put a is equal to 0, 0 raised to power any number is not defined. Okay, so 0 raised to power any number, it will still be a 0. Not defined, but a 0. Sorry, 0 raised to power any number would be a 0. So that's a 0 here. Okay. Next, we go to the negative numbers. Negative 1.5. So negative 1.5 raised to power x. Okay. So, okay, just a second. Okay, to check the nature of this exponential graph when a is a negative number, for that we need to add a minus here. The moment we add a minus and put this, so a is equal to 1, that is fine. As I increase the a, you see, a is equal to 1.1 or 1.3, let's say. This is how it behaves, the function behaves when the base below is negative and the power is as usual, x. So what's happening? Since it's a negative number, so negative 1.3 raised to the power something. So as you keep on increasing the x, the value will increase, magnitude will increase, but in the negative direction. That's why you see the increasing in negative y zone. So overall it's a decreasing function, still a decreasing function. Let's say if we take a negative power, let's do that. So a is positive, we take x as negative, a is for negative x. So now you see, if I increase this a is equal to 2 raised to power negative x, so 2 raised to power negative 1 is a 1 over 2. Okay, 2 raised to power negative 1. So at x is equal to 1, it will be 1 over 2. At x is equal to 2, it will be 2 raised to power negative 2 or 2 raised to power 1 upon 2 raised to power 2, 1 upon 4, which is even lesser. So that's why you see a decreasing function. As x increases, it will be like 2 raised to the power negative 100, which is 1 upon 2 raised to power 100. So 1 upon a very big number, which is approximately leading you to a 0, which is why you see this horizontal asymptote. It's approaching y is equal to 0. Okay, the asymptote is y is equal to 0. Okay, this is fine. Now let's see how to solve inequalities, okay, using Desmos. It's a good use case. I take the first inequality as y less than, or let's say 2y less than 3x plus 3, or 8 less than 3x plus 8. This is the first inequality. Okay. Next, I write y greater than 2x, or let's say 6x. We do 6x. Okay. Y greater than 6x. Let's say we take just this much. Okay. And we're asked the solution. We asked the solution set for this system of inequalities or inequations. Okay. So as you click on these, you can see the point of intersection. Zoom it in. See the point of intersection where these two intersect. Okay. The meeting at x is equal to 0.889. This is where they're meeting. Beyond this, they're not meeting. So this will become the upper bound of the solution set. So 0.889. Let's check the lower bound. Till where is this satisfied? Okay. So you can drag it to see till where this is getting satisfied. Okay. So basically it's getting satisfied for all x less than 0.889. X equal to 0.889. It's getting satisfied for all those. You can check that by further zooming out. Keep zooming out. Even up till billions, it still satisfies. This area still satisfies. So for all x less than the intersection point this is the case. Okay, and we can also see manually, we can see the solution manually as well. So 0.889 and 2y less than 3x plus 8, this gives us, let's check this. Okay, so these are the inequalities. Let's do it one by one. Y greater than 6x is 1 and 2y less than 3x plus 8, so y less than 3 over 2x plus 4. Okay, so y is less than 3 over 2x plus 4, y is greater than 6x. So let's see the solution sets. First, let's find the point of intersection of the two curves. So 6x is equal to 3x over 2 plus 4. Okay, so 6x minus 3x over 2, that's 12x minus 3x, 9x over 2 is equal to a 4. X is equal to 8 over 9, which is 0.889, exactly what we got on Desmos. Okay, but this took time, definitely. Next, let's look at the curves. Let's look at both the curves. We'll try to sketch them manually and see what we get. Okay, so first curve, y is greater than 6x. So y is equal to 6x, this would be a line, it will be a pretty steep line passing through the origin. Okay, and y is greater than this. So which region would it be? This one or this one? For that, here's a trick. Take any point on one of the two regions. Let's say I take on this region. A point on this region would be, let's say, negative 1 comma 0. Negative 1 comma 0. Let's check if this inequality is satisfied. If I put x as negative 1, so negative 6, and y is 0. 0 is greater than negative 6, so this is satisfied. The right hand side area would be the correct one for the solution. Okay, so this is the solution from y greater than 6x. Next, we sketch y less than 3x over 2 plus 4. This equation is going to look like 3x over 2 plus 4. So x is equal to 0, y is 4. Will come somewhere here. Okay, and y is equal to 0, x is equal to negative 8 over 3. So somewhere here, this curve is going to look like this. Okay, and if we extend our initial one, we can identify the point of intersection. There is this point of intersection. Okay, and then what is the solution region for this one? Let's take an imaginary point on its right hand side, 0 comma 0. Let's check for the origin, where the origin falls. So I put y as 0, x as 0, so right hand side is 4 and 0 is less than 4. It is satisfied. So origin is covered in the solution. So this is the solution. So you see the common area, the common solution, or which is actually the solution for this inequality, is this area. So basically all x less than 0.889, which we saw through Desmos calculator. Okay, so x for all x belonging to negative infinity till 0.889. Okay, that's the solution. This is how we solve inequalities. Let's see a few more on Desmos. Okay, let's do another inequality. Let's say we have a more complex one, a quadratic equation. So y, or let's say 3y less than 2x squared plus 4x minus 12. Okay, so as you can see, if I do greater, let's try greater. Okay, so this is the space for the first one, the area inside the parabola, and the equation already given. So click on any of them, you see the points. X is equal to negative 3.34. The solution begins from here, goes all the way till x is equal to positive 3.59. That's your solution set. Simple as that. Okay. We could even take a parameter, a slider here, and see how the solution changes. See, the solution set is shrinking all the way till x equal to 10. And if I take it to be negative, the moment it goes negative, the parabola will flip. At 0 it's linear and starts flipping. But the moment it flips, the solution set is now bigger, because what's inside the parabola is no longer the set, because the function, the equation has changed. Now y is greater for all points outside the parabola. Okay, so this is how you can analyze the nature of the curve. Okay, we've talked a lot about log in the last video, functions part 2. So let's look at a few log functions. Okay, here's an important thing: how to input a log function in Desmos, or any complex function which cannot directly be typed, because with log we also need to input the base. Let's say I write y is equal to log 4. Okay, when I say log 4, it's by default taking the base as 10. But what if I wanted to change the base? I want some other base. Y is equal to ln, or let's say log x. It's taking on base 10. Okay, I want to try another base. So for those things, there are some other controls. These are important, so look closely. So I think this button was not visible yet. You see this icon on the bottom left, show keypad. The moment I click on this, you see a lot of options here. X, Y, these are for writing the equations, facilitating you to write the equations. See, you can input the absolute value function directly from here. And I write mod of x. Mod of x has been graphed here. Okay, so mod of e raised power x, that has been graphed. There's no change. There's no change in mod of x or mod of e raised power x, because e raised power x or mod of x, mod of e raised power x, because the graph is always positive. But the change will be shown the moment you take a function that has some part in the negative area. For example, we can say mod of x minus 4. X minus 4. Okay, this is one. Let's say mod of x squared minus 4. X squared minus 4. See this change? Because this portion of the graph, the middle portion of the graph, was going below the y-axis. That gets taken in the mirror image about the x-axis. This is also part of the transformation. We'll do a transformations video, transformations of graphs video, the next one. Okay, this is part of that. But it can graph from here. Any complex functions you need, you can key in from this functions button. Click on functions. Sine, cos, tan, all trigonometric functions, inverse trigonometric functions. Statistics can be dealt with from here, computed from here. List operators, visualizations like the different plots, distributions. Calculus, in calculus we have the log thing. Okay, so let's do with the base. You see, there's one log with no base, that is base 10. There's ln, which is base e. Then there's log of something to the base a. A is given. So here you can identify the base. Let's say I want to do base 4, and then I do inside anything, x. Okay, so log of x to the base of 4. Okay, let's vary the 4. Let's take 4 as a parameter. So a, add a slider. Let's see what happens. So a is equal to 1. When base is 1, it's not allowed. Log is not defined for base 1. Okay, the moment we increase, okay, let's increase the value of a. 1, 2, 3. Okay, at a is equal to 1, it's not defined. Okay, after 1, 1.1, 1.2, 1.3, you see, goes on. This is how the nature of the graph is changing. This is the log graph. And the moment I put it below 1, you see, the graph gets inverted over the x-axis. That means it has gone negative. The graph has gone negative. Okay, only up till 0. The base cannot be less than 0. So between 0 and 1, this will happen. The negative area would happen. After 1, this would happen. At 1 and below 0, log is not defined. Okay, so here's the thing. Okay, log of log of x to the base a. Let me take an exponential function here. Y is equal to a raised to the power x. Okay. See, they are both mirror images. I've taken a, so it's deriving its value from the slider. That's why purposefully I took a. See, they're both mirror images. Let's vary the a. Both graphs will vary simultaneously. At a is equal to, I don't know what value, they coincide, then they intersect, and this is how they spread. At x is equal, a is equal to 1, they'll both become a straight line. Okay. And then less than that, the graph looks like this. Okay. And here they are mirror images, all the way like this. Okay. So like this, you can input the functions from this button down here. Okay. Any complicated functions. You want to find derivative for any calculus, guys. You want to find derivative of, let's say, let's make a complicated function. Sine inverse of exponent e raised power 4, or sorry, x. This is the derivative. Or let's say sine inverse of 4x squared. This is the curve of the derivative. Okay. Like this, you can put in different functions, check the properties. Okay. An important tool here is the graph settings. You can let go of the grids. So now there are no grids. Okay. The axis numbers, they can be let go of when you just want to see the nature of the curve. For example, now if I write e raised power x, it's just about the nature of the curve, no values. Sometimes even that's needed. You can take arrows which are heading in different directions. This is mostly for vectors. Okay. So then you have the x-axis and y-axis labels. Okay. So the labels can be changed. The step can be changed. Step, if I take 5, okay, and I show the axis numbers, it's taking steps of 5 each. In y, I take steps of 4. It's taking the steps of 4 each. Okay. The label I'm saying, let's say x-axis is for time. It's showing time. Y-axis is for distance, showing distance. See, the labels are changing here. Okay. So like that, you can change certain settings. Then the x-axis, the axes can be linear or logarithmic. Even that is allowed. So logarithmic scales are a bit different. The x and y logarithmic scales would change. Okay, it's for very specific use cases. Till school level, like till year 12, I don't think you need that. Okay. Now here's the by default value in angles. So this here is set to radians. We can set it to degrees or radians, anything. Accordingly, the functions that you write inside would change. For radians, let's say we graph a function. Okay. Let me remove these labels. Right now we don't need them. And I'm removing the step as well, because otherwise it'll keep that. But we can override the step. So let's say you take the step as 5 and 5. Okay. But you can override it the moment you scroll in or out. Okay. Zoom in or out. Let's say we take sine x. Y is equal to sine x. Right now what you see, the x's, they are written in radians. 0, 0, pi, 0, 2 pi, 3 pi by 2, 5 pi by 2. This is because radians is highlighted. Moment I do degrees. Okay. I need to bring it. I need to zoom in further. Why? Because in degrees the values would be a lot different. Okay. So in degrees, when you see, this graph looks very odd. Why? So at 90 degrees, sine will go to 1. Y is equal to 1. But x is equal to 90 and y is equal to 1. They cannot be presented in the same proportionate frame. Okay. Whereas that is possible for radians, because 90 degrees is equal to pi by 2 radians, or 1.57 radians. So 1.57 and 1, they are proportionately near. So the graph looks a bit apt. Okay. So let's change it back to radians, and it starts looking good again. Okay, so this is how you can graph different things. You can make use of inequalities. Let's say y is equal to sine x, we compare it with y is equal to 0.5. It's cutting at all the different points. It'll follow a pattern, because even sine pi by 6 is 0.5 or 1 by 2. This can be changed, this can be varied. You can directly vary and see what's happening. We can make it into inequalities. So let's say I do 3 sine x, and then y is greater than 0.5, becomes an inequality. Okay, and the solution set of this inequality would be all the sets. It will be a repeating set, so basically all x's, at all x's it's happening. Y is equal to, y is greater than 0.5. let's do y is less than 3 sine x. Now it becomes an apt inequality. So now there's a pattern. It won't be satisfied for all x's. So -6 to 0.5 union 0.16 to 0.5 union 6.4 to 9.25. See, so 0.16 to 2.97, 6.45 to 9.25, 12.73 to 15.5, like this. Okay, so more or less we've covered everything that's required on Desmos. You can solve integrals, you can do calculus here, you can plot different graphs or statistics, but this is from a point of view of a high school test. This would be more than enough. Okay, it's all you need to know about Desmos, but make sure you practice and make it a habit to solve most of the questions through Desmos in order to have incredible speed on the test. Okay, so we'll meet with another video. The next one would be on transformations, so stay tuned, subscribe, like and comment. Okay, bye bye.